So imagine that you buy a brand new commercial airplane, a Boeing 737 for $100 million. Imagine you're on a plane from New York to London with 300 passengers. The flight is smooth, the service is perfect, the food is served, and the plane touches down safely at Heathrow. But instead of taxiing to the gate, disembarking the passengers, refueling, and getting ready for the return flight, the pilots taxi the plane right into the English Channel, open the doors, sink it to the bottom of the ocean floor, and the airline immediately buys a brand new $100 million aircraft for the next flight. That sounds completely insane. No one could survive that. No transportation system could possibly scale under those regulations. For the first 60 years of the space age, that was exactly the unquestioned business model of every rocket company and government space agency ever. Every launch was a complete write-off. We'd build these big, complicated machines, fill them with fuel, fly them once for a couple of minutes, and then throw them away. The booster, the expensive engines, the guidance systems, the structural metal, the fuel tanks, all were headed for the bottom of the ocean, or burning up in the upper atmosphere. Space travel was still prohibitively expensive, because the capital outlay for a new vehicle was amortized over a single flight. It was an extraction mechanism designed to consume capital, not save it. But the real math of getting around in space has changed, and it hasn't changed because of some sudden breakthrough in thermodynamics or metallurgy. It changed because of a change in the unit economics. Today we look at the direct math showdown between the legacy expendable rocket model and the reusable model pioneered by SpaceX. The numbers behind this shift show why the old space monopoly busted, how SpaceX built a huge cash flow engine, and what this means for the incentives of capital-intensive businesses. You want to know how a startup disrupted a multi-billion-dollar government monopoly? You have to look at the unit economics of the hardware. Let me show you what the numbers really say when you take into account the variables nobody in the transaction has an incentive to mention. What we do here matters more to the future of the aerospace economy than any marketing campaign or political speech. This comparison took 3 weeks of running actual 26 numbers, current launch contracts, orbital launch database records, and manufacturer cost disclosures. Think of this as the spreadsheet I wish someone had shown me before I made the same decision with less information. What I'm about to walk through is not my opinion. The mathematics. The math cannot help it. It doesn't matter what option seems better or what rocket looks cooler on a launch pad. It cares about the input, it cares about the output. Inputs are publicly available contract values, estimations of manufacturing cost, and recovery logistics. The outputs are what nobody ever shows you. They are the real margins, the capital efficiency, and the cash flow that pays for future growth. This comparison includes only real numbers from institutional sources, including the Federal Aviation Administration's launch reports, NASA budget filings, and commercial contract disclosures. No ifs, no cherry-picking time periods, no unstated assumptions. It's just the two systems, side by side with all the costs on the table. You may be surprised by the result. When I first ran the numbers, it surprised me. For decades, the aerospace industry was dominated by a few giants, who told us that the only way to fly was to throw away rockets. The mathematics tells a very different story. We will walk you through every cost, every operational fee, every amortization schedule, to reveal the truth about how reusability rewrote the rules of business. Building a rocket and throwing it away after each launch is the ultimate capital efficiency failure. What we are proving today is simple in its essence. Reusability is not an environmental or marketing strategy. It's a brutal unit economics business strategy that collapses the marginal cost to reach orbit, creating a massive cash-generating flywheel. The legacy space contractors did not build expendable rockets because that was the only engineering answer. They built them because their business models were geared towards maximizing government spending, not minimizing operational cost. When you look at a space launch system, you have to apply a lens of capital preservation. If you throw away the hardware, your marginal cost is connected to the manufacturing cost of the whole vehicle. If you recover the hardware, then your marginal cost is limited to refurbishment, recovery logistics, and fuel. The cost of manufacturing decoupled from the cost of launch creates an economic moat so wide that no expendable competitor can cross it. This is the system map of today's space economy. One side is the legacy model, based on cost-plus contracts and throwaway hardware. On the other hand, there is the reusable model based on commercial contracts with fixed prices and recoverable stages. To grasp why one of these systems is now devouring the other, we need to run the numbers on both. Let's start with the legacy system that owned the sky for half a century and trapped us in a high-cost bind. Let us now look at the legacy expendable model. For years, the commercial and government launch market has been dominated by a joint venture between Boeing and Lockheed Martin called the United Launch Alliance, and the European consortium Arianespace. Their main workhorse vehicles were the Atlas V, the Delta IV Heavy, and the Ariane 5, now replaced by the Ariane 6. The math of an expendable launch is simple and brutal. When United Launch Alliance launches an Atlas V rocket, the base cost of that launch is between $110 million and $160 million. If they use a Delta IV Heavy, a big vehicle used for heavy government satellites only, the cost goes up to $300 million to $450 million per launch. An Ariane 6 launch costs Arianespace somewhere between $80 and $120 million. And where does that money go? It goes right out into the ocean. The first stage booster, with costly rocket engines, burns for less than 3 minutes before returning to the atmosphere and smashing into the Atlantic. It burns up completely in the second stage, which accelerates the payload to its final orbit. The payload fairings, the half cones that surround the satellite during launch, are jettisoned in sync. To make matters worse, United Launch Alliance had a special contract with the United States government called the Launch Capability Contract. Under this contract, the government paid them about $1 billion a year just to exist, to cover their enormous overhead and keep their factories open, whether they fired a single rocket or not. This was a huge cash drain that prevented them from being competitive in the market. The same inefficiencies are at work in the European Ariane program. Ariane 6 is manufactured in several countries, with factories in Germany, France, Italy, and Spain. This geographical distribution is not determined by the efficiency of manufacturing, but by the need to reach a political consensus among the member states of the European Space Agency. The parts have to be sent by sea and air to French Guiana to be assembled. This huge international shipping supply chain adds tens of millions of dollars of overhead to every single launch. This is a permanent increase to the baseline manufacturing cost of the expendable rocket. And the production cost of those vehicles is the rock bottom for the launch cost. If it costs $80 million to build the metal cylinder and the engines, you cannot sell a launch for $50 million. The legacy players are locked into a high-cost, low-cadence loop because every launch involves building a brand new rocket from scratch. They can't lower prices because their marginal cost is tied to the physical manufacturing process. For every single mission, they have to sustain a huge network of factories, suppliers, and skilled labor in order to build a new rocket. This is the definition of a consumption business model, where capital is destroyed on each transaction, and customer has to pay for destruction of the asset. Now we look at SpaceX Falcon 9 reusable mode. The Falcon 9 is a two-stage rocket, but the economic structure is completely different. Let's have a look at the manufacturing cost of a brand new Falcon 9. The total cost to manufacture a new Falcon 9 is estimated at about $50 million. That first stage booster that holds 9 Merlin engines and the main fuel tanks is about 60% of that total cost, or about $25 million to $30 million. All these Merlin engines are built in-house, giving 190,000 pounds of thrust that combined gives more than 1.7 million pounds of thrust at liftoff. The second stage with a single vacuum-optimized Merlin engine costs about $10 million. The nose cone halves, the payload fairings, cost about $3 million each, or $6 million for the pair of them. The other $4 million is for assembly, integration, and checkout, all $50 million for a single expendable launch. But SpaceX does not fly the Falcon 9 as a throwaway vehicle. Instead, after the first stage booster separates at about 80 kilometers, it executes a series of engine burns, deploys grid fins to steer, extends landing legs, and lands either back at the launch site or on a drone ship bobbing in the ocean. Drone ships, named things like "Just read the instructions" or "Of course I still love you," function as floating recovery pads. Meanwhile, the two halves of the fairing deploy their guidance systems and parachutes, gliding back to Earth to be scooped from the water by specialized retrieval vessels. Of the $50 million rocket, SpaceX recovers the $30 million booster and the $6 million fairing halves. The only hardware lost for good is the $10 million second stage. SpaceX changes the basic math of the launch by recovering $36 million of the $50 million in hardware. The manufacturing cost is no longer a recurring sunk cost for the booster and fairing. It is a capital asset that can be depreciated on a per-flight basis. Let's take a look at the amortization math over a series of launches to see how this plays out on the ledger. We will observe how a repeatedly flown booster turns into a financial printing press. Let's do the amortization math on one Falcon 9 booster. Imagine if SpaceX makes a new booster for $25 million. If the booster is considered to be a one-shot asset, the hardware cost is $25 million on the first flight. But if that booster is recovered and flown a second time, the manufacturing cost is spread across those two launches. The cost of the booster per flight is down to $12,500,000. 3. By the 5th flight, the manufacturing cost allocated to each flight is only $5 million. By the 10th flight, it's $2,500,000. And by the 20th flight, which SpaceX routinely gets to with several boosters in their fleet, the manufacturing cost of the first stage that goes to that launch is only $1,250,000. Same math applies to the payload fairings. A pair of fairings flown once costs $6 million, a $6 million pair. The hardware cost per flight is reduced to $600,000, flown 10 times. Now we put in the second stage, which is always disposable. That $10 million is the same cost on every flight because it is not recoverable. The hardware cost on the 20th flight of a Falcon 9 is therefore $1,250,000 for the booster, $10 million for the second stage, and $300,000 for the fairings. The hardware cost for that launch is $11,550,000. This compares to the $50 million of hardware cost on the first flight, or the $80 million to $160 million of hardware cost for an Expendable Atlas V or Ariane 6. The cost to manufacture each launch has dropped by more than 75%. This is the power of compounding utilization of assets in a capital-intensive business. You make the physical manufacturing process a secondary concern with 20 flights of the same hardware. Your competitors are still in their factories building replacement parts. The booster doesn't need a full rebuild between these flights either. SpaceX engineers run a series of tests, including ultrasonic scans of the weld joints to check for structural fatigue, checking the engine valves, and a brief test fire on a special stand. They have optimized this process, and the turnaround time is incredibly fast. They can fly a single booster multiple times in a single quarter. Of course, reusability is not for free. Space fans are often enthusiastic, and hidden variables are not taken into account. We have to take them into account to understand the real margins. That's the first thing. The performance penalty. When you try to land a rocket booster, you can't burn all the fuel pushing the payload into orbit. You'll need to reserve a large amount of propellant for the boost back burn, the re-entry burn, and the final landing burn. This fuel reserve is heavy, so a reusable Falcon 9 can only deliver about 30% less payload to orbit than it could in a fully expendable configuration. If a customer has an extremely heavy satellite that needs the absolute maximum performance of the rocket, SpaceX must fly the booster expendably, throwing it away. But for 90% of commercial payloads, the reusable performance is way more than enough. Second, there are costs for recovery and refurbishment. When a booster lands on a drone ship, it must be secured, then towed back to port, moved into a hangar, and inspected. Back then, this refurbishment process took months and cost millions of dollars during the early days of the Falcon 9. Today, SpaceX has perfected the process, such that a booster can be turned around in less than 3 weeks, with refurbishment costs estimated at between $1 and $2 million per flight. Thirdly, the cost of the recovery fleet. SpaceX has several drone ships, rocket recovery vessels, and tugboats. You have to spread out the capital cost of building this fleet of ships, including the specialized ships with giant cranes, to lift the 15-story boosters off the drone ships. Finally, we have to look at the fuel itself. A Falcon 9 uses rocket-grade kerosene and liquid oxygen. The total cost of the propellant for one launch is on the order of $200,000 to $300,000. For a multi-million-dollar launch, the fuel cost is a rounding error. And even with $2 million for refurbishment, $1 million for recovery fleet operations, and $300,000 for fuel, the marginal cost to launch a reused Falcon 9 is only about $15 million. This includes the $10 million second stage, which is expendable. Even when you take into account the performance hit and the recovery overhead, the numbers still very strongly support reusability. The legacy contractors tried to use these overhead costs as a reason why reusability would never work, but forgot to run the real numbers. Now let's take a look at who benefits from this economic inequity. SpaceX does not sell its launches at its internal marginal cost of $15 million. That would be giving away the economic rent of their technology. Instead, a commercial Falcon 9 launch costs about $67 million to $70 million. That price is intentionally low enough to beat out every other disposable on the planet, but high enough to make enormous profits. Let's calculate the gross profit on a reused commercial launch. Commercial price, $67 million. SpaceX's internal marginal cost, $15 million. Gross profit, $52 million. Gross profit margin, greater than 77%. That's a far cry from the legacy aerospace contractors. Arianespace charges $90 million for an Ariane 6 launch. If their manufacturing and operational cost is $80 million, then their gross profit is $10 million, which is a margin of just 11%. If ULA launches an Atlas V for $140 million and they cost them $110 million, their margin is 21%. SpaceX is making software-like gross margins, 77%, on industrial physical hardware. They are using this huge cash cow to build two capital-intensive projects: Starlink, their global satellite internet constellation, and Starship, their next-generation fully reusable launch system. The legacy players are caught. They can't cut prices to compete because they'd be selling at a loss, less than what it costs to make. SpaceX could drop their prices tomorrow to $40 million and still have a 60% gross margin while putting every competition out of business. This is the be-all, end-all, competitive moat 100%, driven by the collapse in unit cost of reusability. Let us compare the financials over a long-term horizon. Take a telecommunications company or a government agency, for example, that needs to deploy 100 medium-sized satellites over the next decade. If they go with a legacy expendable launch provider like United Launch Alliance, who use the Atlas V at an average cost of $103 million per launch, then the total cost for 100 launches is $13 billion. All that $13 billion goes to making hardware that is immediately dumped into the ocean. The legacy provider makes a small profit, while the customer is charged the full cost of the hardware consumption. If they opt for Arianespace with Ariane 6 at an average cost of $90 million per launch, the total cost for 100 launches is $9 billion. Again, the hardware is consumed and destroyed on each flight. Let's now consider the SpaceX alternative. If they fly on a reused Falcon 9 at a commercial price of $67 million per flight, the total price to the customer is $6.7 billion. The customer saves between $2.3 billion to $6.3 billion compared to legacy options. But the math inside SpaceX is even more dramatic. In real terms, that means $15 million per launch, or $1.5 billion to do those 100 launches. This means that SpaceX takes in $6.7 billion in revenue, spends $1.5 billion on operations and expendable second stages, and nets $5.2 billion in gross profit. That $5.2 billion is free cash flow that can be put back into research and development. Meanwhile, while the legacy providers are spending their time and money building 100 duplicate boosters to replace the ones they destroyed, SpaceX is using their $5 billion cash cushion to build Starship, a vehicle designed to be fully reusable, including the second stage. Not only is the throwaway model more expensive, it is a financial dead end that starves the company of research and development capital. Reusability is a system that accumulates capital over time. It is a wealth preservation system. Expendability is a constant drain. If the math is this clear, then why didn't anyone in the aerospace industry build a reusable rocket before SpaceX? Why did Boeing, Lockheed Martin, and the government agencies keep wasting billions of dollars in hardware for 60 years? The answer is in the alignment of incentives, the structure of government contracting. The space launch industry for decades worked under cost-plus contracts. With a cost-plus contract, the government pays the contractor for all the documented costs of developing and building a rocket, plus a guaranteed percentage in profit. Consider the incentives this creates. If a contractor is assured an 8% profit above his costs, how does he increase his total profit? They have to charge more. If building a rocket costs $100 million, they make a profit of $8 million. If they can redesign the rocket to cost $200 million to build, then their profit goes up to $16 million. Efficiency is a tax on money. Reusability, which reduces costs, would reduce the contractor's revenue and profit directly. The legacy players had a huge financial stake in ensuring rockets were costly and disposable. In addition, the programs were politically protected by the distribution of jobs. NASA's giant expendable rocket, the Space Launch System, has parts made in every state. Boeing and other prime contractors intentionally spread subcontracts out to the largest number of congressional districts. When a politician tries to cut funding for an inefficient rocket, the contractors remind the politician of the jobs that will be lost in the politician's home district. The system was designed for political consensus and budget extraction, not for cost-effective engineering. The cycle could only be broken by an outsider funded privately and working on fixed-price commercial contracts, focusing solely on minimizing unit cost. In the context of the broader lobbying efforts of the aerospace industry, the numbers are mind-bogglingly obvious. The big defense contractors have spent hundreds of millions of dollars in the last 20 years lobbying Congress to keep cost-plus projects alive. They have made the case successfully that reusability was a high-risk, unproven technology that could endanger critical national security payloads. They made this argument to justify their high-cost contracts and to delay the introduction of competitive fixed-price models. It was no engineering failure, but an extremely successful effort to protect profit margins at the expense of the taxpayer. The commercial space market has hit a tipping point. Reusability has so distorted the economics of launch that the expendable rocket is going the way of the dinosaur for all but specialized government missions. Expendable launchers are crazy expensive. Commercial satellite operators answer to their shareholders. They have to manage their own capital efficiency. Why would they pay a $90 million premium to launch on an expendable rocket when there is a reusable option for half the price? Research institutions, foreign governments, and telecom companies are shifting their payloads to SpaceX. This has led to a monoculture in the launch sector. Arianespace is having trouble landing commercial contracts for Ariane 6 and is almost completely dependent on European government mandates to keep it alive. United Launch Alliance is retiring the Delta IV Heavy and moving to the Vulcan Centaur, which is still mostly expendable and can't compete with the cadence and pricing of the Falcon 9. SpaceX has established a launch monopoly by capturing the commercial market. This monopoly is not grounded in exclusive legal rights or regulatory protection. It's based on unit economics. They are playing a different game until a competitor can land a booster, inspect it, refuel it, and fly it again in under 3 weeks for under $2 million. They are trying to operate an airline where they buy a new aircraft for every flight. SpaceX just refuels and takes off again. The old monopoly has been completely destroyed by the spreadsheet. The lesson of the rocket math goes far beyond the aerospace industry. It's a foundational framework for evaluating business, technology, and capital allocation. When you're looking at companies to invest in or build, you have to ask yourself, is this business model expendable or reusable? Are all transactions considered as recurring manufacturing costs, or are they building capital assets that can be utilized over and over again? This is why software companies have been able to demand such high valuations in the past. A software developer writes a block of code once the capital expenditure and sells it 1 million times over. The marginal cost of distributing that code is almost zero. Software is the most reusable asset. Traditional manufacturing or retail is an expendable model. Any car company that wants to sell a car has to buy the steel, pay the labor, and use the energy to build another one. In physical terms, their margin is always bounded by the cost of goods sold. SpaceX did something special. They took a historically disposable physical manufacturing grind business and made it into a reusable asset system. They tailored the software economics to the physics of space travel. As you evaluate your own investments, look for companies that are proactively converting consumption costs into capital assets. Look for the platforms that can use their infrastructure, their code, or their distribution networks to drive down their marginal costs. The math of reusability always beats the math of consumption, whether you are launching satellites or building a personal stock portfolio. The Space Launch System was designed to burn capital, insulated from market forces by government incentives and cost-plus monopolies. SpaceX spotted the misalignment, focused on unit economics, and built a 77% gross margin moat that is currently reshaping the satellite economy. The defaults of the aerospace industry were set to benefit the contractors and not the customers. They rewrote the whole system to turn the hardware from a disposable cost into a reusable resource. And when you look at the horizon of technology and business, the lesson is clear. The winners are not the companies with the most hype or loudest marketing. They are the ones that reset their engineering to the brutal reality of unit economics. The board is there. The math is done. The reusable asset has the advantage. I'm Scott, and this is the math of reusability.